Well, we are live. Welcome. Welcome, everyone who is viewing our presentation today. We are the University of Oregon. The Summer Academy to Inspire Learning SAIL program is hosting our weekly Faculty Live and Learn presentations. I'm Laura Fernandez, the Executive Director of the SAIL program, which is a UO pre-college program serving the state of Oregon. We are honored to have with us today two UO physics faculty members, Eric Corwin and Jayson Paulose, talking about how everyday stuff conceals centuries of old physics problems that continue to be relevant and challenging today. I can't wait to hear more. Jayson Paulose will be starting with us today first, and he is an assistant professor in the Department of Physics and a member of the Institute for Fundamental Science and the Material Science Institution at the University of Oregon. Jayson received his PhD in 2013 at Harvard University. After postdoctoral appointments at Leiden University and UC Berkeley, Jayson joined the physics faculty at the University of Oregon in 2018. Jayson leads a research group which utilizes theoretical and computational approaches to understand complex phenomena in living and artificial systems. Eric Corwin will be joining us next, and Eric is an associate professor in the Department of Physics and member of the Material Science Institute at the University of Oregon as well. Eric received his PhD in 2007 from the University of Chicago. After a postdoctoral appointment at New York University, Eric joined the physics faculty at the University of Oregon in 2010. Eric leads a research group which uses experimental and computational approaches to study the statistical mechanics of disordered systems, including glassy and jammed systems. Can't wait to hear more about that. During this session today, for all of you viewers, our faculty love questions. So please enter your questions into the chat at any time. And as soon as we have an opportunity, they will offer some Q&A opportunities for you. We are looking forward to hearing all about what they have to say. So Jayson, we welcome you and are excited for your presentation.
Thank you, Laura. Thank you very much for the invitation. I'm really excited to be talking here with all of you today. I wish I could have seen who's actually here, but I'm just talking to a screen, and I'll try to imagine you all behind the screen somewhere, where you are. Before I get started on what I wanted to talk about today, I just wanted to give a couple of minutes, a 2-minute introduction to my research group and to what I do here at the University of Oregon. So I'm a theoretical physicist, which means I perform computations and often using computers, sometimes using pen and paper, and trying to understand how systems in the world work. And today I'm particularly going to be talking about trying to understand mechanics. Trying to understand how objects move, how they deform, how they bear weight or load, and how we can use physics and mathematics to design new materials, new objects with maybe desirable mechanical properties that let us do something interesting, maybe have a material that can bear loads in a different way than typical naturally occurring materials. On this slide, I just had a few examples of the kind of computations I might do. So there are 3 pictures here. The details are not important, but each of them is some kind of calculation that tells us how a particular structure deforms. Up on the left is a lattice of flexible beams. Think of them as little rods that are connected in a particular way. That they can bear loads in some places and they can move in other places. And on the right, top right, is something very similar, another computation I made a few years ago of a structure that deforms in a particular way. And down at the bottom is, again, a computer simulation the results of a calculation done on a computer for how a very thin sphere, think a ping pong ball, actually deforms when you push on it or poke on it. And as a theorist, what I do is make computations, do these calculations, but I also like to connect these to real world objects that we can build and we can probe and see if things in the real world follow the results that we predict here. So here are actual images of experimental work, which people either I work together with experimentalists who can build these things that I calculate. Here, this is actually one that I have an example of here. So here's a structure built based on the design that I show here. And it actually deforms in the way that we calculated it to behave. Out here is a structure made out of iron beams and gears that has the motions in it. You can actually build the structure. Here's a colleague of mine showing how the structure can bend and deform in the way that we actually predicted it to do. And down here is a picture from a microscopic ping pong balls that a colleague of mine was able to make. Each of those spheres here these are pictures from a microscope. Each is basically a ping pong ball, but really, really tiny, about the size of a grain of sand. And you can see how that those ping pong balls, even though they're really tiny, they behave like how we expected them to. So this is to give you an idea of what working in theoretical physics is like. We make calculations where we try to connect with things that people actually can build and probe. But today I wanted to tell you not really about any of these, but about something that might seem in some sense even simpler. I wanted to talk about paper. So here I'm going to give you around 20 seconds to grab a few pieces of scrap paper you might have lying around, maybe junk mail or things that your homework from last week. Don't use your homework from this week. I don't want to get in trouble with your teachers. But just simple sheets of paper. We're gonna try a few things with them and see how physics and mathematics connects with how paper behaves. How it bends and how it can be stiff when you want it to. So when we think about paper, we typically think we don't think of it as very strong. It's floppy. It barely holds its own weight. Here's a regular sheet of paper, printer paper. And that's true, but in some ways, paper is actually quite stiff. And what I mean by that is if I take a piece of paper and I try to stretch on it, it actually doesn't stretch at all. If you took a sheet of rubber or a thin sheet of plastic that were this thin and you pulled on it, it would stretch out by a lot. But paper is actually quite strong against stretching. So in some ways, it's weak. In some ways, it's strong. And so the question is, can we use the strength of paper to stretching, and can we turn it into strength in terms of bending? Can we use one type of strength of paper to make it strong in another way? And the answer to that is we can. And to do it, what we need to do is use geometry. So geometry is the mathematics behind shape. It's how we describe different shapes in the world, like the shape of the sheet of paper as I'm trying to bend it and do various things with it. So the key to making paper stiff, which maybe some of you have actually used in some way or another, is actually to put a fold or a bend in it. So if I take this floppy sheet of paper, and you can follow along at home, if I roll it up into a tube, and this is something you probably have experienced, if you roll up a sheet of paper for a poster or something like that, you actually get something that's pretty stiff. It's not floppy the way your unrolled sheet of paper was. You can even push on it a fair amount, and it pushes back. So we made paper stiff in a way that it wasn't before by putting a fold in it. And so the reason for that, the reason this actually works, actually goes back to some mathematics that was figured out in the 1800s. It goes back to a mathematical theorem that was proven by the mathematician Carl Friedrich Gauss in the 1800s. And what Gauss figured out, you can write down equations that basically say, if you translate those equations to real life, they basically say that a sheet of paper, if it's folded in one direction, or if it's curved in one direction, so here I rolled it in one direction, it becomes very stiff in the other direction. So along this direction, which is not the direction that I folded it, it now becomes really hard to bend. It becomes really stiff. So that is a geometric, a mathematical fact that translates into something real that we can hold and that we can experience, the stiffness of a roll of paper. So so this feature is called, sometimes it's called in physics, it's called geometric rigidity. It means you're using geometry, you're changing the shape of this sheet of paper to make it rigid, to make it physically strong. Now, geometric rigidity sounds fancy. I'm telling you about theorems from over 100, almost 200 years ago. But actually, in some ways, geometric rigidity is something I think many of us know about. I just realized what I was planning to do is actually stop sharing so that you can see better what I'm doing. So this is geometric rigidity, and it makes paper stiff by putting a fold in it. But I think most of you are actually quite good at geometric rigidity, or many of you might have used it in your daily lives. And that's because I use it all the time when I'm eating pizza. So I really like pizza. I like thin crust pizza, which it turns out I actually got pizza for dinner yesterday. This was just a coincidence. I didn't plan it for this presentation, but we have pizza in our house once in a while. And here's a piece of thin crust pizza. And as many of you who've eaten pizza might know, if you pick up a piece of pizza straight out of the box, especially when it's hot, it's floppy, right? It doesn't hold its shape very well. And that means that often, if it's a hot piece of pizza, you get the sauce falling onto your plate or onto your shoes. You get the cheese sliding off, and that's not a great way to eat your thin crust pizza. But the pizza aficionados among you might already know that there is a simple way to deal with this floppiness, and that is to use what I like to call the fold hold. Maybe you know the fold hold very well. If you don't, be prepared to have your mind blown. You take your floppy slice of pizza and put a fold in it. And when you do that, voila, that slice of pizza is not floppy anymore. It's nice and straight. And here you're using geometric rigidity. You took something that was flat, like a sheet of paper, and just like the sheet of paper was floppy, but if you put a fold in it, you can try this again with your sheet of paper, put a fold in it as if it were a slice of pizza, and now it becomes stiff in the direction that's perpendicular to the fold, in the direction that you haven't folded it. And it's stiff enough that you can actually, put something heavy into this sheet of paper and it can hold it up. So you've made this paper and you made pizza stiff by using geometry. So think about that the next time you're having thin crust pizza, if that's something that you enjoy. Okay, so moving on. So here's something else we can do with pizza is we can put a fold in it, not a simple curve or a bend, but you can actually make creases and fold it up. This is what you would do if you made a paper airplane. It is what is behind the Japanese art of paper folding. You may have heard of origami, which is the art of taking a piece of paper and folding it in particular ways so that you can get beautiful shapes like paper cranes or really fancy paper airplanes. It turns out that this is another way to change the mechanical behavior of something thin like paper. So here's a sheet of paper. I started out again with one of these sheets of printer paper. If we had more time today, I'd have shown you how to make this, but I made this morning And at the end of the talk, I'll show you, I'll give you a link on where you can learn how to fold this yourself. This is actually a sheet of paper that's folded up in a particular way. And it's a particular origami fold called the Mura fold, named after its inventor. And what's special about this fold is, if I take this folded up piece of paper, you see it's actually a bunch of creases in particular ways. And if I hold this sheet of paper at two places, and I pull, the sheet of paper unfolds, and you can see it's actually one full, 8.5 by 11 sheet of letter paper. But there's one smooth motion. The folds in it are made in such a way that, just like an accordion, it can fold in and out while I'm only holding it by these two ends. It's a very controlled motion. So this fold is special because it lets us pack things into really small spaces, and very carefully, but in a very controlled way, open them up when we need them to open up. And there's actually only one way the sheet of paper can open and close because of these folds, and so that way we don't make mistakes. And this actually, it looks like I'm just having fun with paper. But the underlying physics, the underlying ideas are actually used in designing satellites. So why is that? So here, I'll go back to showing you another picture. Back to my slides. Here is an example of a satellite. Actually, it's a satellite sent up by the Japanese Space Agency in the 90s. And it's called a space flyer unit. And what you see here is actually a piece of the satellite solar panel. So each of these squares in this picture is a stiff solar panel made out of probably something based on silicon. So each panel can't fold up, but they broke up this large solar panel into many little pieces. And if you look carefully, you see each of those pieces has this kind of parallelogram shape, like the squares in my pattern here. And it was built in such a way that that large panel could pack up, could fit neatly into a rocket capsule and be sent out into space, where when it was the right time, the solar panel could unfurl in a very smooth, controlled way. And so this is an example of using origami to design a better satellite, one that works much better out in space, where you really have no room for error. You can't go and fix the folds if it doesn't unfold in the right way. Here is another example. This is a prototype from NASA, which is called Starshade. It's also based on an origami fold, not quite the one that I just showed you, but a different one. And this one's also built so that it can be made really compact and can unfurl to block out the sun. If you have space instruments that are very delicate and that need to be protected from sunlight, you could use a sunshade, what they call a star shade, to do that. And down here is actually a picture of you can fold the NASA Starshade design in paper as well, starting with a sheet of paper. And you can see that it's just like this piece of paper here. It's something that folds up really small, and in one smooth motion, it opens up. And that's something that you can use to send this out into space and have it work well. Okay, so the last thing I wanted to do with paper is something that I do sometimes at the end of the day if my calculations don't work out. I take a sheet of paper and I crumple it up. So I invite you all to do the same. Find one of your pieces of scrap paper, not your homework, and crumple it up. And that seems like a pretty violent thing to do to this poor sheet of paper. I'm not sure why I deserved that. But now what I want you to do is take that crumpled sheet of paper and uncrumple it. Smoothly, crumple it nice and good, and then smoothly uncrumple it. And try to get it kind of flat as possible. So what we've done is we've started with a smooth sheet of paper, and now we've made it really wrinkled. And actually what we've done is put in a whole lot of these little folds that make the paper stiffer just because of geometry. You've put in a lot of geometric rigidity into the sheet of paper. And notice this crumpled and uncrumpled sheet of paper actually is much less floppy than the sheet of paper I started out with. It's actually, you've found another way to take paper and make it stiff. And so this is another form of geometric rigidity, put in a lot of wrinkles to make something stiff. And so you might ask, okay, so what can we do with this? That's great, but I don't do very much with this sheet of crumpled paper. But it turns out that there is actually also a reason to understand these things, and it connects with some of the most advanced new technologies that scientists are thinking about today. So to give you an example of that, here is a picture. I want to introduce my colleague, also at the University of Oregon, Professor Benjamin Aleman. He's an experimentalist, and I'm a theorist. Now, in physics, we all know that the experimentalists are the cool folks. Look at that. Look at that lab coat. Look at those goggles. That's not how I look when I go to work. So Professor Aleman is really, really good. He's an experimentalist, and he's one of the world's experts in building drum heads. Not just ordinary drum heads, but really, 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 really tiny drum heads. Here's a picture of one of Professor Aleman's drum heads. So it's really a sheet of material that's stretched out, just like the head of a drum, and it would vibrate if you hit it, just like a drum would, but it's really, really tiny. This whole drum head here is about 1/10 of the diameter of a grain of sand. So this is a picture from a microscope, an electron microscope, actually, and that's the only way you can see it. And what's even cooler is that not only is it small, it's extremely thin. It's only 1 atom thick. This is made of a material called graphene, which is a single layer of carbon atoms that are all connected together in a very particular way that gives you a sheet. So Professor Aleman builds these things, and as a theorist, what I try to do is understand their mechanical properties. In this case, I basically want to understand if you hit this drum head and you could listen to it with a really, 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 really tiny microphone, what would it sound like? At what frequency would it vibrate if you hit this drum head? And it turns out that if you do the calculation, you write down the equations for that kind of thing, and you assume that the drum head is really flat, you get the wrong answer. You don't get the actual sound that you expect for the drum head. And the reason for that is if you could take this picture and zoom even further, use an even stronger microscope to look at a really tiny part of this and blow it up, what you would see is that it's actually not flat, it's wrinkled. It's wrinkled just like the sheet of paper that you just crumpled up. And that makes it stiffer than you would expect if it had been not wrinkled. And so to get the right sound out of this drum head, when we're trying to calculate how it sounds, we need to put in the wrinkles. Otherwise, we don't get the right answer. So this is why it's important to keep track of what your wrinkles, what your crumples are doing. So that was it. That's what I wanted to say today. I have a couple of links up here if you want to try some of these origami projects at home. But thank you again for giving me the chance to talk, and I'm really curious. I'm really happy to take any questions that you might have about what you saw. Thank you.
Wow, thank you, Jayson. That is, I will never look at a piece of paper the same way again. I know we have some questions in the chat, but I was just really curious when you were talking about the drum heads. Are we talking about literally drums? Or what is a drum head?
Yes, so literally what I mean by a drum head is the part of a drum that vibrates. So the skin of the drum. And Professor Aleman builds, you can think of them as little drums. The reason he builds them is to control vibrations in a material. So if you're trying to build, say, a better ultrasound machine, you need to be able to control how sound goes through a structure or material. And building those drums in the right way, connecting them up in the right way, helps you make, say, better ultrasound devices or better microphones that can record vibrations from the outside world but maybe in frequencies that regular microphones don't do a good job with.
Wow, thank you. Thanks for clarification. Well, you do have some questions in the chat.
Okay, so here's some questions. Okay, so I'll go through the, well, there are a lot of questions at once. I'll try to break them up. So one question was, what interested you in studying teaching physics? So for me, it was, growing up, I really liked, I enjoyed doing mathematics in school and also physics. And I was just curious about how things work. And when I went to college, what I realized was that you know, a physics career is a way for you to basically do more of asking, hey, why does something work the way it does? And being able to pursue that and trying to understand that using mathematics. And so that's it's when I realized that, you know, what I always thought of as something, you know, fun and cool to do could actually be a job. That's when I realized that maybe this is what I want to do. In teaching physics and also doing physics research. And so questions, have you been asked physics questions by students that you couldn't answer, and what were they? Oh, all the time. So I can't even think of an example of what these questions are. So this is, I think this is something that's very important. Even, you know, physicists at all levels, there's no sense in which we know all the answers to all the questions. So first of all, you know, doing physics research, if you're doing research, you're really trying to answer questions that nobody knows the answer to. So in some sense, it's fundamental to my job that there are questions that we don't know. So until a few years ago, for instance, we didn't know that those really microscopic drum heads, the reason they were stiffer than they are, we didn't know that it was because of wrinkles. So 10 years ago, if somebody asked anybody in the world, you know, why don't these drum heads sound the way they do? No physicist could answer because they didn't know the answer. It was through the process of research that we actually got to now our best understanding of why things work the way they do. So that's one answer. And the other answer is that even in the classes that I teach, you know, I try to learn as much as I can about the subject when I teach it, but there's no way in which I know everything. Being a good physicist is not really about knowing everything. It's more about being able to know, figure out where to look, or figure out what kind of calculation to do to find the answer to a question. So I have questions, I get questions all the time that I don't know the answer to. But I think what I try to do in my job is, you know, direct the person to where they could find the answer, or ask, you know, what should I do to find the answer? And that's, in some sense, that is what physics is about, more than just knowing what the answers are. Okay, here's a question about jobs in the field of physics. Maybe that's something we can talk about towards the end, because I'm sure Professor Corwin also has ideas. I'm going to look at some of the other questions. What other parts of our daily lives are affected by physics that we might not think about? That's a great question. And the answer is really pretty much everything. You know, in some sense, physics really is about understanding how everything behaves. So the next thing you pick up, you know, maybe before this talk, you didn't think that, you know, picking up a piece of paper and folding it up was, you know, physics in any sense, but it really is. And that's just because physics is how we describe the world. So really everything. I don't have any neat examples right away, but they're all around us. There's a question, do we have to be good at math that is more advanced than geometry for physics? That's a great question. So there's no, again, it's similar to the question about whether we know the answers to all questions, or there's no way in which I know all the math in the world that's needed for physics. What I try to do is, if there's a problem, I try to, and I'm trying to solve it, I'm trying to understand how a piece of paper works. Then I ask, okay, what what math might help me to solve that problem. So often in physics, we do use math all the time, but the type of math we use really depends on the problem. And there are many problems for which instead of using kind of math at a very detailed level, what we're doing is using, say, computer programs. So some of my colleagues are really great at writing computer programs that do the math for you. And so you don't necessarily have to sit down and do the math. So math is an integral part of physics, but again, there's no sense in which you need kind of a comprehensive understanding of math. I mean, that's just like no physicist knows all physics, no physicist or even no mathematician knows all of mathematics. But again, the key is knowing what math you need to learn, or maybe not learn yourself, but have somebody explain to you or work with somebody who can do it for you. I think that's more the key for physics. Okay, so in the interest of time, maybe will some of these questions be here and we can come back to them at the end? Does that make sense? Because I know it's just past 11:30.
Yeah, I think that makes a lot of sense. Maybe we should switch over.
Sounds good. Well, welcome, Eric, and thank you so much, Jayson.
All right. So, hello, everybody. As said, my name is Eric Corwin. I'm a physicist. I've been working and teaching at the University of Oregon now for about 10 years. And what I want to talk to you about is that the hardest geometry problem in the world is at the bottom of a bucket of sand. And what I mean by this is if you think of the actual bucket of sand, very similar to what Jayson was talking about, its mechanical properties, so the way that it feels and the way that it acts, are controlled by its geometry. So I want to pose a really simple question to you. So in kindergarten or elementary school, you were all taught about the 3 states of matter, right? If you have a solid, you can push on it and it pushes back. So, you can stand on a brick. If you have a liquid, you can pour it into a bucket and it will take the shape of the bucket. And if you have a gas, you can put it into a container and it will just absolutely fill the whole container. So which is sand? So you might say, oh, it's obvious, sand is a solid because look, there's this person and they're standing on sand. And it's true, you can, fill a bucket with sand and you can stand on it. But you fill that bucket with sand and then you can pour it out into your little castle mold and it takes the shape of a castle. So obviously sand is a liquid. And then you can take that, sand and you can put a little bit of it into a bucket and you can put, your frisbee on top of the bucket and shake it all around and the sand absolutely fills the whole space. So sand is obviously a gas. And so the answer is no, sand isn't quite any of these, and it's the geometry that controls it. So to understand this, we have to go to a much easier, but still extraordinarily difficult question, which is what is the densest possible packing of little chunks of things? So like oranges. And if you've ever been in a very fancy grocery store, I don't know, maybe they do this in Whole Foods in Eugene. They probably do it somewhere, though I don't see it done very much because it takes a lot of effort. But if you've ever been in a fancy grocery store, you will see that the oranges are always arranged in this pyramid. And this pyramid is a very particular structure. It's called a face-centered cubic crystal, which is a complicated name, but it's what you would do if you want to fill the most space with oranges. And in fact, it fills, about 3/4 of space. It takes a lot of effort to make. If you've ever worked in a grocery store and had to do this, it's not particularly fun. And back in 1611, Johannes Kepler was commissioned. Somebody actually paid him money to figure out what is the densest way that I can pack cannonballs together. They wanted to know, if we're shipping cannonballs on a boat, we want to get our money's worth. We want to put as many cannonballs on the boat as possible. That way we can be the best at war that we can be. So what is the densest possible packing? And so way back in 1611, Johannes Kepler thought, oh, well, it's obviously the same thing you do with oranges, although I guess they didn't have oranges in Europe at the time. But it's this same structure. And he told them, he got paid. He said, I'm pretty sure this is it, but I can't prove it, right? I can't think of anything denser, but I can't prove that this is the best. So this was it took all the way until 1988 for this gentleman, Thomas Hale, to prove that this structure, now done with tennis balls, is the densest possible packing of spheres. And now this proof is crazy difficult. This proof was in fact the first computer-aided proof. And so what Thomas Hales did, he came up with a computer program that would come up with about 100,000 different statements. And then the computer program had to go through systematically and show that each statement was true. And so this was his proof. And it was, it was kind of controversial within this weird math world, because they all hated it because they wanted to be able to look at a proof and understand it, and they just couldn't. So it took a team of about 5 or 6 people who, the term is refereed, but who tried to determine whether or not Thomas Hales was correct. So they spent about 8 years, not full-time, but on and off, they spent about 8 years. And at the end, they were only able to say, we're pretty sure it's true. So this is a really, really hard geometry problem. What is the densest possible packing of spheres? And we think we have an answer, but oh my goodness, is it hard. So much harder is a problem attacked by the Reverend Stephen Hales, who lived in 1677 to 1761. And I should point out he has, as far as we know, no relation to Thomas Hales. So the Reverend Stephen Hales was, apart from being a reverend, he was also a scientist, and he was interested in food. And you might ask, food and plants, and what possible connection does that have with the packing of spheres and sand? And the answer is he wrote an entire book called Vegetable Statics, or an account of some statical experiments on the sap in vegetables, being an essay towards a natural history of vegetation, also a specimen of an attempt to analyze the airs, blah, blah. They really had long titles back then. But what he did was he took a bucket and he filled it with peas, right? Just regular, peas. And then what he did was he filled that bucket with hot water and essentially cooked the peas and put a weight on it. And what happened is the peas, as they cook, they swell. And as they swell, they run into their neighbors. So you started out with this packing of spheres. And then by cooking it, he turns those spheres into a shape that's totally constrained by all of the neighbors around them. And so this was a way of studying the structure of this random packing, this pile of peas, which, if you think about it, is really hard, right? If I give you a pile of peas or a bucket of sand, and I tell you what is the geometry of, the peas that are all around one little pea in the center, that's going to be really, really difficult to answer. How do you possibly look inside of a bucket of peas? And so his brilliance was to realize what you can do is you can deform the peas, and that allows you to then take apart this packing pea by pea and see the shape. And so he was able to measure things like the number of contacts per particle, which is to say, if I'm a pea in there, how many other peas am I touching? He was able to measure how much area or how much volume each particle has available to it, all in the 1600s. So that then brings us farther into the future. This is the 1800s. A scientist, James Clerk Maxwell, who is famous for Maxwell's demon. And this is actually a statue that's on the side of Willamette Hall if you come and visit the University of Oregon. I'm not going to tell you about Maxwell's demon, but if you're interested, look it up. It's kind of fun. Instead, I'm going to tell you about Maxwell's criterion. So Maxwell started to think about these packings of spheres geometrically and mathematically. And the ideas that he came up with are very approachable. He said, if we're going to have a bucket full of peas, say, And those, we put a lid on it. And so none of those peas will move when we shake it. That means that every pea must be held in place by all of its neighbors. And so now we can just think about what are the different ways that a pea can move, and we need to keep it from moving that way. So a single pea can move up or down, it can move left or right, or it can move forward or back. So on average, we need to constrain each of those motions. And so you can use these ideas and reanalyze the Reverend Hale's experiments on peas, and you can look at the number of contacts that each pea has. And so Maxwell would predict that each particle, each pea, should have 6 contacts. And so this is not actually the data from peas. I got lazy and I did this on a computer rather than actually building a bucket and filling it with hot water and peas. But I measured, I took, a bunch of spheres in the computer and I squished them together, and I measured how much is each particle touching its neighbors. And what I found was, no, not every particle has exactly 6 neighbors. Some have only 4, some have as many as 10, but on average, they have exactly 6 neighbors. So we can begin to understand something about the small structure of the way that these spheres, these peas or sand, get squished together just by thinking of sort of very simple geometry and math. And the beauty of this is once we start to approach random packings, it means that we can approach any random packing. So this is a huge, I think it's an Olympic-sized pool filled with those little balls that you find in ball pits. And that should have the exact same geometry as a bucket of sand and the exact same geometry as a pot full of peas that we're cooking. So in other words, what I'm saying is that there should be something universal, something that is just always true in every situation in which you have sort of these random amorphous, and amorphous just means sort of structureless packings of spheres. So one thing that's surprising is if we do this, if we look at a bucket full of sand or a bucket full of ball pit balls or a bucket full of peas, they always fill about 64% of space. And this happens every time. And so this is a puzzle, right? Kepler was able to show, and then Hales was able to prove that the densest we can do is 74% of space. But why is it that if you just take all of those oranges and you get sick of your job stacking them and you just throw them into a big box, they'll fill 64% of space? And so there was a question asked of Jayson, are there questions about physics that you don't know the answer to? This is one. I do not know why it's 64% of space. I can tell you why it should be less than 74%, because obviously when we throw them in randomly, it's not the best. And I can tell you why it should be bigger than 0, because I put some balls in and so they fill some space. But this particular number is crying out for an answer, and I don't have one. And this is, the simplest possible question you can ask about this hardest geometry problem in the world, and I can't even answer that. So these are examples of all sorts of things that can be modeled as spheres. So one is obviously a bucket full of marbles. Another is giant sand dunes. These are microscopic colloids, so like little, grains of silt. And then we can even model glasses as packings, amorphous packings, not now of spheres, but of actual molecules. And we spend a lot of time thinking about that, but I'm not going to talk much about that today. The key is that we think that every random packing is in some sense the same. So if we can understand one, we can understand all of it. So granular materials, things like sand or ball pits, are a really good system to study experimentally because they're easy. You can hold them in your hand. Like we said, they're not a solid or a liquid or a gas, and the geometry determines absolutely everything. So one example of the strange things that happen from granular materials is if you go to a beach and you're walking on wet sand, what do you see when you step down? You create this little halo of dry sand around you. And that feels absurd. You're taking this wet sand, you're pushing it down, so you should be pushing it into the water, and instead it gets dry. So why does this happen? We can try and answer that by thinking about how sand has to change when we move it. So when you step on the sand, you're pushing the sand out of the way. But in order to push the sand out of the way, it needs to push its neighbors out of the way. It needs to slide over its neighbors, like this beautiful animation. So particles can't move unless lots of other particles move as well. You'll notice when they slide over, they create a bigger gap. So when you step on the sand and they slide over, all of that water can drain into there. This is an animation. We took a bunch of beads and we cut them out of this complicated material called a photoelastic material, which is really just plastic. And then you just look at it through polarized light. And polarized light is fascinating in its own way. What you see is wherever you get forces on the plastic, it will light up, it gets brighter. So you can see as we stress and strain and move these grains, they initially had no forces, they were totally happy. And then we push on them and they develop this complicated and changing network of forces. So this is another feature of these granular materials that we can try to understand through geometry. And then the example, which I promised, is this. So if you have a bunch of, of baking soda, you can also do this with baking powder, it doesn't matter, you just need any kind of a powder, even flour ought to work. Take that and pour it quickly into a cup. So here I've done that, I've poured it quickly into a cup. I can't do this very well in person because it happens quickly, but I had a high-speed camera, so I was able to film this very, very quickly. If you do this in person, you will see it, but it just doesn't get captured well over Zoom or YouTube. And what you do is drop a marble into it. So here you see a marble dropping in, and it creates this beautiful crater, right? And that's sort of what you expect when you go to the beach, and then, oh my gosh, what is that? We dropped a marble into this baking soda and it created a little crater, and then a huge jet of baking soda came back up. So, I've seen this before, but the first time I saw it, I was absolutely floored. This is, insane. This is so weird. I've never ever seen this happen at the beach, but if I quickly pour some baking soda into a cup, I could play this again for you, drop a marble into it, I get what I expect, which is a little splash of baking soda. And then I get something I don't expect at all, which is this huge jet. So we can do more careful experiments, and we did. And so this was the biggest jet we were able to make. We made a big cylinder and we filled it with fine powder, and then we actually bubbled air through it to make it as loose as possible. And then we dropped a big marble into it. We got this jet. The fat part of the jet was about 10 inches, and then it had this sort of spray of little droplets that went up nearly a meter, went up about as high as we had dropped the ball from. And then we thought, okay, well, if we think about, when we're walking on the beach and we step on sand, it needs to spread apart and the water drains through it. So there's something similar going on with air. So we did this at 3 different pressures, from atmosphere to vacuum. And you can see as we remove the air, this jet gets smaller and smaller until with no air at all, it's just a tiny little nothing of a jet. Let me play that again. So we thought, okay, probably the air does matter, but what we'd like to do is see what happens actually in this packing. So if we were Hales, we would try and understand it by, making this out of peas and then cooking them. But that's too slow. This happens quickly. This happens in the blink of an eye. So instead, what we did was we tried to look beneath the surface using X-rays. And so we went to this place, the Advanced Photon Source, which is an amazing name, at Argonne National Labs, which is right outside of Chicago. And this is almost like a chest x-ray or a dental x-ray, except we took those x-rays at 6,000 frames per second. This is a lot of the detail of sort of how it's all set up. I don't need to go into it, but basically what we did was we drop a particle into a tube of sand and we could watch what happens underground. We had to stitch it together because we could only take little slices of images at a time, but still we were able to make measurements here from atmosphere down to vacuum. You can see what happens. So in atmosphere, we drop the ball and it tunnels creates this huge tunnel, and then that tunnel collapses. And right here where it collapses and comes together, you get this concentration of the flowing sand, and that shoots this jet upward. And you also saw a little jet downward. You get this bubble of air rising up. So it really acts a lot like a fluid. If we decrease the pressure, we see that the ball gets stopped a lot quicker and we get a smaller void. And if we decrease pressure even more to vacuum, the ball gets stopped entirely and we don't get much of a jet at all. And our reasoning was that it's this same dilation, that when you have air, it almost acts as little shocks or springs between every grain of sand. And so you can't compress the sand, instead it gets pushed out of the way. And so you get easy flow. When you remove the air, all you do is you compress the sand at the end, and that's that. And so the conclusion for this little bit is that sand can flow like a fluid, and then air pressure really matters for determining the behavior of sand. And so I think with that, I'll probably stop and try and answer some of the excellent questions that have been posed. So there we go. Let me stop my sharing. There we go. So thank you for listening. So a question is this the same as when you push down on your skin and the skin becomes white? Is that the blood moving away from the pressure, just like the water moving away from the sand? In some sense, it's very similar, right? You're pushing on something and you're pushing it away. So when you push on your hand and your hand, you push all the blood away, there you've actually pushed on the blood. The difference with the sand is that we have these two different materials. We have the sand and the water. So we push down on the sand and we really do compress and push the sand away. But in doing, we also make all of these extra little gaps between the sand. And so the water is able to drain out into those. So it's sort of similar and different in various ways. So other questions. So one really fun question, do you think we'll ever have all the answers for how the world works in terms of physics? Or do you think we'll always be learning new things and proving ourselves wrong? This is a really deep and difficult question, right? So on the one hand, I think, behind physics is this idea that the world is fundamentally knowable. But then there's a question, are there a finite number of things to know about the world? Or are there an infinite number of things to know about the world? If there's a finite number of things, if in the end we know 100 things and there are only 100 things that entirely determine the universe, then probably we could figure them all out. But if they're an infinite number, we'll always be finding new things. My personal gut feeling is that we're always going to be finding new things, that there are always sort of new and interesting sorts of complications and interactions that arise. And to push this idea, I want you to think about how many of the things in your everyday life humans just don't really all the way understand. Right? There are lots of very sort of mathematically difficult things that we understand, but a lot of the stuff that you do every day, we just don't know. So as an example, we don't know why sand fills 64% of space. We don't know why if you are moving grain around and you pour it into a hopper, sometimes it gets stuck and jammed. We don't know how to predict that. There are so many things that we don't even have a beginning of a handle on that I don't think we're ever going to get to an answer. And Jayson, please, jump in on any of these questions. So other fun questions are, what jobs may I look to are possible in the field of physics? So there are lots and lots. Obviously, you see Jayson and I, so doing research and teaching is one possibility. You can also do what people talk about as industrial research. So if you think about sort of all of this thinking about sand, this was actually started by oil companies. They were the first people to really invest a lot of effort in understanding sand. And part of the reason is that there are huge stores of oil in what are called tar sands. So it's sand permeated with oil. And if you want to understand how to extract the oil from that sand, you need to understand the geometry of sand. You need to understand the same sort of things that you understand when you step on wet sand and it drains out the water. So industrial research. And then, nowadays, of course, if you get good at physics and also are able to program, there's a whole world of data science and analytics available to you. If you get good at physics, you can go into financial, sort of the finance industry, doing modeling. In some sense, in my opinion, an education in physics is really an education in sort of creative analytical thought. So marrying together the creative thought of, how do I come up with new questions? How do I test ideas? With the analytics of, how do I answer things mathematically? How do I demonstrate that something is true rather than just it feels like it's true to me? So having that ability to engage in this creative analytical thought, I think opens a lot of doors. So other questions, there are a lot more subgroups to physics than I thought. How did you discover the subgroups that you're most passionate about? That's an excellent question. And I'll answer it, and then Jayson, you should answer it as well, because I'm curious. So for me, I went to college knowing that I was really interested in physics, but I thought that I was interested in high energy particle physics. And I actually got to work on, particle physics experiments. I got to spend a summer at Fermilab at a giant collider. And what I realized was I kind of hated it. That, I loved the big ideas, but what I was doing every day was just boring. I just didn't like it. I thought it was kind of no fun. But while I was there, the person who I was working with had a friend who was studying this granular materials stuff and was telling me about it. And I just absolutely loved it. I loved the fact that it was these questions that we could have asked 500 years ago, but nobody had thought to sort of engage in them with as much effort and rigor as people were putting into high energy particle physics. And I thought, that's what I want to do. So it was really just happenstance, who I happened to know at that time that got me into this. So Jayson, what about your answer to this?
Sure. Yeah. So I actually went into college thinking I would be an engineer. And it was partway through college when I was also taking physics classes with my engineering major that I realized that, I was really I found really appealing kind of a more fundamental level of understanding than you would need in engineering. So for me, I was drawn to research that was kind of at the interface where I was trying to understand fundamentally how things work, but also trying to make connections to some kind of technology, to some kind of real material or a real structure that could have some impact out in the world. Then again, like Eric, I also really got to know which subgroup I liked by trying out a few different things. So I took every chance I could to do research rotations in different professors' labs. And I realized I was not good at experimental physics. I couldn't work in a lab. I worked well with computers. I worked well with doing calculations. And in that subfield, I tried to find, I worked in 2 or 3 different groups before finding the one that eventually led to what I study now. So yeah, so there's kind of the ideas, and there's also the actual practice of doing it, and that the best way to learn that is just by trying out different things, doing research rotations, and whenever you have chances to do that.
Wow. Go ahead, Eric.
No, nothing.
Well, I was just going to say, you both have blown my mind on a whole different perspective of physics, but I sure hope all of our viewers take away the importance of asking questions and the power of doing this, the analytics and the research. And um, physics is, you have opened my eyes to all these new and different ways of looking at the world that even I hadn't even thought about. So I'm certain you have opened many eyes today to new areas. And it's lovely to see both of your approaches to physics are very different as well. So your examples really brought things to life for us, and we're very honored, like I said, to have had your time and have you share this with us. We recorded the session today, and it will be posted on our website by tomorrow, so anyone can view the session at a later time, or you can share with I know I'm going to share with my own children, so I hope it gets shared around. Again, thank you both so very much for taking this time. And we hope you have a wonderful rest of your Wednesday.
Thank you. This
Thank you
was a
very much.
pleasure.
Awesome. We'll be in touch. Thank you. Take care. I